this section, we are going to talk about how to use the linear model to actually predict some real-life data. So for example, in this table, it lists the average monthly temperature and electricity cost for Texas home in 2008. This table displays the values rounded to the nearest whole number. Make a scatter plot, and how would you describe the correlation? So if you look at the data as it is right now, there are 3 columns. One is the month, the second one is average temp, and the third one is electricity bill. So then you ask yourself, which one is X and which one is Y? So remember, X means independent variable. So independent means it does not depend on something else. And then Y means dependent variable. So dependent means that it does depend on X. So you ask yourself, which one would be independent and which one would be dependent? So electricity bill depends on the temperature, because usually what happens is if it's hot, then you would turn on the AC, and so the electricity bill would be higher. So then we can say that the average temp is X and the electricity bill is Y. Then you ask yourself, what does the month represent then? Well, months are just the actual data points that you have. So you have a point from January to December, and they don't have to actually represent X or Y, because the other thing you can look here is that it says it's the monthly temperature and the electricity cost in a home. And so basically this monthly part is not actually something we care about at this time. So the month doesn't matter. Okay, so now just recall how to graph a scatter plot. This is X, this is Y. So really this 61 and 150 is the same as saying 61, 150. Just a point like that. So let's really quickly have you pause the video and then graph all 12 points. Okay, after graphing 12 points, your data probably looks something like this. It doesn't have to be very precise, because what we're looking for is, like the question said, what is the correlation? All right, let's talk about correlation really quickly. There are 4 types of correlation, and it relates very much to the slope. So weak positive is kind of the first type we're going to talk about. Actually, there are 2 very general types. It's either positive or negative. And then there's something called no correlation, which basically just says that there's no relationship between the 2. All right, so positive means that it has a positive slope. So if you kind of remember slope, how slope looks like, it's a positive slope. Negative means negative slope. So the difference is between weak and strong. So what is a weak positive and what is a strong positive? So weak positive means that the data looks like it's going in the positive direction, meaning there's some kind of trending in the positive direction, except it's kind of weak. Kind of weak means that most of the data are not together in a line. Strong positive means that most of the data together looks like they are more or less in a line together. So if you can't really tell the difference between the weak positive and strong positive, what you can do is something like this. If you draw a line through it, a line that you think best fits this graph, you ask yourself, do I have more points close to that line, or do I have more points far from that line? So you can see that in the weak positive, there are some points that's kind of far from the line, right? And then if you look at a strong positive, you can see that most points are actually quite close to the line. So then that is the biggest difference between a strong and a weak correlation. So let's look at weak negative and weak positive. So same idea. Both of them are negative, which means the trend is going downward, except one of them is weak negative, meaning they're kind of far away from each other but trending down, and a strong negative means that they're mostly together trending down. Again, if you were to draw a line through it, you would have more points together for the strong negative, and then more points far from that line if it's weak negative. No correlation means that there is just in general no trend. So kind of looks like a blob of data, and there's just not in general no trend going on between those data points. So then this red line that I was drawing is actually called the line of best fit. So what does that mean? That means the line that best fits all the data points. So a line that basically can go through or predicts most of the points. So let's look at this example that we drew here, or the scatter plot that we have. If you were to draw a line through 2 points, any 2 points you pick, that you think will best represent this data, which 2 points would you pick? And there is no one right answer. However, there are some bad answers, but there are several good answers. So for example, I probably would pick these two. I don't know which month they represent, but if I were to draw a line through it, I think it goes through most of the points pretty well. So I would probably say that's a pretty good line of best fit. Now, what's a bad point to pick, or bad 2 points to pick? Well, definitely these two, right? If I did that, I can create a line, but it doesn't go through any point except for those 2 points. So that's a very bad representation of the data. And especially since you can see that the data is trending positive and my line that I just created is trending negative. And so this is not even predicting the data anywhere close. So this would be a example of really bad data. Now, if you ask me are there 2 points that you have to pick? No. You don't have to pick the same points as everybody else. There is no one right answer. You just have to say why you pick those 2 points and how does that line that you created the most represent the data. So that's called the line of best fit. So let's go ahead and do another problem just like that, and this time we're actually going to calculate the line of best fit. So this one, same idea. This one is a word problem on predicting the median home price. Median home price is just kind of saying how much homes cost in Florida. So this says, what is the equation of a trend line that models the relationship between time and home prices? That means find the line of best fit. And then we're going to use the equation to predict the median home price in 2020. So if you look at this table here, again, you ask yourself, what is X and what is Y? Well, the year is X and Y is the median price. And why is that? Because the price of the house depends on the year that it's in. So what you can do, again, is plot this as a scatter plot. So go ahead and pause the video and graph these 7 points. All right, you can see the points kind of look like this. So again, which 2 points would you pick to represent a line of best fit? For me, definitely don't pick these two, right? That's creating a very, very bad line. But what's a good line? I'm not sure. I'm going to pick the first and the last. I think those two create a pretty decent line. So now you have 2 points. The first point is the first year I have, so 1940, 23100. And then the last point is 2000, 105,500. So then from these 2 points, can you create a line of best fit? Of course. All you need is a slope, and then you just need one of the 2 points to create a line. So I'm just going to use these 2 points. So the slope is going to be 105,500 minus 23100 over 2000 minus 1940. We probably should use the calculator on this one because the numbers are so big. And you can either leave it in fraction or calculate it to the decimals. If you are going to use decimals, meaning you're going to divide it out, you should try to round to the 3 places after the decimal, because the more places after the decimal that you keep, the more accurate the data. So you don't want to round right away. Okay, so 1373.333. I think that's pretty good. Okay, now the line of best fit. So we're going to start with point slope form. All right, I'm going to pick the lower point because that just means the numbers are smaller. All right, so you probably have never really had to work with numbers so big and so, I guess, not nice, but it's kind of the real life situation. A lot of times you don't get very nice numbers. Minus 2664266.02. All right, add the 23100, you get 373.333x minus 66.02. All right, so this is a prediction. Now you ask yourself, what is this line? Does this line look reasonable? So remember that this is the slope and this is the y-intercept. So the y-intercept is negative, basically, what is this? 2 million. So you might ask yourself and say, like, I'm not sure if this is the right line because it looks like I'm not actually going through negative 2 million in the y-intercept there. Or am I? Well, actually, if you look at our graph as it is, you see how here, this is not the origin. The origin would be 0, 0, but this is not 0, 0. You see how here is 1930? I am not actually anywhere close to 0. So if you kind of think about it, my line is actually going to go straight to the bottom left a lot more than the graph is showing. So the graph is not actually starting at 0, 0 because you see this is 20,000. This may be 0 on the y-axis, but then on the x-axis, it's not starting at 0. And therefore, if I actually drew this graph according to the way it should be, then it would cross negative 2 million on the y-axis. Either way, the question next asks, they want us to use this equation that we created to predict the home price in 2020. So home price in 2020, home price, remember, represents, or y is representing the home price, and then the year is represented by x. So that just means when x is 2020, what is y? All right, so let's try that. So we have this line that we said represents most of our data because it creates a trend line to predict the home price based on the year. And now that I have a good line that I can trust, I'm going to extrapolate and predict what the home price would be in 2020, since I don't have data on 2020, but I can use the data in the line I have to predict 2020. All right, so put 2020 in the x, and then put it in the equation. So 1373.333 times 2020 minus 2641166.02. 132,966.64. All right, the last thing you always should do is you always should ask yourself, does this data or does this answer make any sense at all? So if I look at my data and say 2020, well, this is probably 2010, and then 2020 is probably somewhere there. It says that I would probably cross through here. Is that the number I am predicting? Looks about right. So this is, what is this, 100,000. This is about 132,000. I think I'm pretty good. So my line, my calculation is good, my line is good, and this prediction makes sense. All right, time for you to practice. So you're going to graph this and you're going to create an equation for the line of best fit, how accurate you think the line of best fit is. So what you can do is graph this kind of, you don't have to create a very, very nice graph. You just want to see, are my points going up? Are my points going down? Which 2 points do I pick that I think would represent the data the best? So you don't want to pick 2 points that's going to create a flat line if it's not a flat data. The second thing you're going to do is after you create that line of best fit, you have this equation. You want to use it to predict what's happening in 2020. Okay, so go ahead and pause the video and try it. Now, I cannot actually give you a accurate, or we cannot actually check each other's answer because none of our answers would be the same. It's going to depend on which 2 points you pick. But you can ask yourself, does my answer actually make sense? So again, your data is going to, your line of best fit is going to depend on which 2 points you picked. So for me, I picked the first and the last. And so my line of best fit ended up being y equals 0.112x minus 221.126. And from my line of best fit, my expected price in 2020 is going to be $5.11. Does this make sense? It's a little bit high, but from the way I was calculating, yeah, my calculation is accurate. I'm not sure if it makes much sense to pay that much for a whole gallon of milk this year. And I don't think anybody is paying $5 for a gallon of milk. But if you pick 2 other points that maybe are closer to the data, you're getting, about $4, which is kind of how much everybody is paying for a gallon of milk these days. So anyways, this is kind of just the idea, which is you have this data, you create a line of best fit based on your understanding of the data, and then you use that line to predict something else. Okay, in this section, we're going to talk about the families of functions. So starting this chapter, what's going to happen is we're going to learn about transformation every single chapter, because every chapter we learn a new function, and then we apply this transformation on all of these new functions that we learn. So since we're going to learn a new function every chapter, we have a name for all those functions. It's called the parent function. It's called the parent function because it's the original function. So before we start changing it, this is the parent, and then after we change it, I guess we don't really have a name. I guess it could be the child, but basically the parent function is the original function. So let's look at this graph here. This is my parent function, which is this red one. And what you're going to do is these 4 activities. A, use the blue color and move this graph to the right 2 units. B, use the green color, move this red graph, so the original one, don't change the blue one anymore, the red one, down 2 units. C, use the purple color, reflect the red graph around the x-axis. And then lastly, D, use the orange color and then vertically compress the graph by half. So think about D. D is kind of the most complicated one. So go ahead and try this, pause this video, and try these 4 graphs. All right, let's go ahead and check your answers. So I would say that A, B, C, you have no problem. The last one, the orange color, vertically compress it by half. So you're probably asking yourself, what does vertically compress actually mean? Vertically compress means whatever the y coordinate was, you're going to shrink it by half. So let's look at, basically you can see that there are really 4 points on this original red graph, right? So we have 2, 2, 4, 4, 8, 4, and 10, 0. So what does it mean by vertically compressed? We're going to shrink the y-coordinate by half. So basically take the y-coordinate, so remember y-coordinate is this part, and we're going to divide by 2, so it shrinks by half. So instead of the first point, 2, 2, instead of 2, 2, it's going to be 2, 1. The second one, instead of 4, 4, it's going to be 4, 2. And then same thing, 8, 2. And then 0, it just stays at 0 because you can't compress that anymore. And so this is the orange one. All right. Now what we're going to do is we're going to do the same thing with a table. So let's kind of color code this. So the first one is the blue color. The blue color, what we did was we moved to the right 2 units. So remember that I was labeling those 4 points, 2, 2, 4, 4, 8, 4, and 10, 0. That's these 4 points down here. So what we're going to do is we move to the right 2 units with the blue color. And so moving to the right actually affects the x-axis, right? Because we're going left and right, that is the x-axis. So moving to the right 2 becomes 4, 2. And this becomes 6, 4. 10, 4, and last one, 12, 0. Pretty intuitive, right? The next thing is, what is this? Green color. Use the green color and then move it down 2. Down 2 means we're going to shift up and down. That is the y-axis. So when we move this down 2, it ends up being 2, 0. So we're not moving the x, so x stays the same. And then the y moves down 2. All right, the next one, we moved by going in the reflecting x-axis. Reflect x-axis is maybe a little bit trickier, so let's go ahead and look at our graph. So here you can see that this is 2, negative 2, 4, negative 4, 8, negative 4, and then 10, 0 remains 10, 0. So then what do you notice on this? You basically take all the y parts and then you made a negative on it. All right, so let's go ahead and write this down and then we'll kind of do the discovery later. And then the last one, the orange one. So what we did was we said we basically shrunk the y by half. So we took the original x, we kept it the same, but then we took the y and then we divided by 2. All right, now if we call the original function f of x, then the blue one, what we did was we moved to the right 2. We moved to the right 2. And so what we did was we moved the x to the right 2. This is a little bit tricky. What we're going to do is we took the f of x, we move it to the right 2. So we basically added 2. Add a 2. Add a 2 to the function, so like that. Now what I'm going to do is I'm going to actually put a minus here because the way the function is written, which I'm going to show you in the next page, is that it actually is the opposite sign of the direction you're actually expecting to move. So this one is a little bit tricky, so we're going to come back to this one. The green one, we moved down 2. Down 2, remember what happened was we took the y value and then we subtracted 2. Now, if you remember, f of x actually represents y, right? Because x represents x, and then f of x means the function depending on x, and that we called y. And so what we did was we took the y value and we subtracted 2. Next, the purple one, what we did was we reflected the x-axis. Reflecting the x-axis, as you can see, made the y negative, or basically took the opposite value of y. And so what happened was we can represent this in telling that whatever y you get, put a negative on it. And then that will reflect it over the x-axis. And the last one, what we did was the orange one, we took the y values and then we shrunk it by half. So basically we took the y value and then we divided it by 2. And I know the x1 is, the moving right 2 is a little bit strange. So we're going to look at how it looks like actually on a function. So this is kind of the general transformation equation, and this is kind of the one that you really should memorize, kind of the basic idea, but it becomes really intuitive after the next chapter or at the end of this chapter. So f of x is going to be your basic function. So every function we just call that f of x. And you can see that there are some letters, right? We have this h, we have k, and we have an a. So what do they actually do to the function? So h, well, actually, let's start with k. K is a little bit easier. K means the up and down movement. So this is, if k is greater than 0, then our function is going to go up. If k is less than 0, then our function is going to go down. And then h is going to be the horizontal translation. So it goes left and right. This one is a little bit tricky. So when you see x minus h, you're actually going to go to the right. So I know a lot of times when we see negative, we're thinking, oh, left. That's usually true, but in this case, it's actually the opposite. So you have to kind of force yourself to remember it's the opposite. When it's x plus h, you're going to go to the left. And then a has 2 functions. So when the absolute value of a is greater than 1, it's going to stretch. So it's going to pull this function like a rubber band in the vertical direction. So it's going to make it longer in that way. And then if it's between 0 and 1, then we say it's compressed. It's kind of like someone pushing it down and squishing it down so that it's flatter. Now I said that a has another function because there could be a negative there. And so if there is a negative on the outside of the function, that is called reflect x-axis. And then if the negative is inside the function, then we say that is reflect y-axis. Okay, so let's look at some examples. This one says, determine the transformation of the parent function f of x. So parent function in this case is just a very general function we call f. And so this one says, g is basically f plus 6. So now you have to ask yourself, this plus 6. Plus 6 is, which letter would that represent? A, h, or k? Well, the 6 is outside of the function. Outside of the function meaning this is the function, this is outside of the function. So then that would have to be k. And then k has to do with up and down, vertical translation. So 6 is a number that's greater than 0. So then we would say that is moving up. So this is move up 6, or you can just say up 6. Okay, I'm going to do 2 more, and then you can do the last one. This one, 0.25 times f of x. 0.25 is which part? A, h, or k? That is a, because it's a number that's multiplied to the function. So that is a is 0.25, and 0.25 is this part, stretch or compress. The question is it stretch or compress? Well, we have to put a in absolute value, and so it is still a positive 0.25, so this is going to be compressed. So compress by factor of 0.25. Okay, I'm going to do one more, and then you're going to do the last one. So this should be number 3. G of x is equal to f of x plus 1 minus 2. All right, we already know that this 2 has to be k. Now this plus 1. So remember I said this is the confusing one. So when you see a x plus 1, we're actually going to go to the left. Okay, so when we see x plus h, we're going to go to the left. Left by how much? Left by 1. So this is going to be down 2 because k is -2, and then we're going to go to left 1 because this is x plus 1. All right, go ahead and pause the video and try number 4. All right, go ahead and check your answer. Hopefully you got that right. So now we're going to bring in some parent functions. So first we have y equals x, which is our linear function. So this is the line. The x squared is our quadratic function. We're going to spend a whole chapter on this. So quadratic function, or this is the shape of a parabola. So if we're not familiar with how these functions look like, we can graph them and check. So we would take out our xy table and then just plug in some numbers and check. Usually I start with -2, so some negative numbers, definitely put some a zero in, and then go up to 2. So these are, easy numbers to check. All right, if it's y equals x, that means y is exactly the same as x, so then this would just be the same numbers. And then we graph them, -2, -2, -1, -1, 0, 0, 1, 1, 2, 2. So this is a line like this. Quadratic. So every time you have an x, this thing says square it. So this is going to be -2 squared. Please don't write this. This is not the same as what we're talking about. We need to make sure this is in the parentheses. So then the whole thing gets squared. And so this is 4, not -4. Okay, -1 squared is the same, so -1 and then square it, which is 1. 0, 1, 4. All right, so then that means I have a point at -2, 4, -1, 1, 0, 0, 1, 1, 2, 4. And then this is my parabola. So these are my parent functions, and what we're going to do now is actually write the transformation based on the parent function. So for example, number 1, given the parent function x squared, write an equation for the transformation of left 3 units. Left 3 units. So ask yourself, left is what letter? A, H, or K? Going to the left, we know that has to do with H. But going to the left. Left is what? +3 or -3? It's going to be +3. The parent function is x squared, so then what we're going to do is take this function and square it. So this is going to be our transformed graph. So basically, we're saying this part, this part gets squared. So we moved it to the left 3, and then we square it. So this is basically the parent function squared. Yes, move to the left 3. Okay, let's go ahead and have you try number 2. If you have this parent function, write an equation of going up, vertical stretch of 2, and then you go down 5. Okay, go ahead and check your answer. This is 2x minus 5. This next one's a little bit tricky. So what it says is, what can you do to f to get g? So this is f. You're trying to get to g. What kind of transformation do you need to do in order to make that happen? So go ahead and pause the video and try to think about it before you look at the answer. So if you have a function x over 2, the question is how do you get there? And then once you figure out how to get there, then you can think about the transformation. Well, so kind of do it one step at a time. So how do I get x over 2 to become, let's just kind of forget the negative. How do I get to 2x? How do I get from x over 2 to 2x? Well, I got to multiply by 4, right? That's going to give me 2x. And then there's a negative on the outside, so let's just attach a negative on the outside. And then the last thing is I'm going to add 4. So then if you kind of clean that up, you're going to get negative 2x plus 4. Now let's go ahead and, I probably should do this in a different color. So I multiply by 4 and then put a negative and then I put a plus 4. So now these red parts that I just put in, can we translate that into a transformation? The first thing I did was I multiply by 4. Multiply by 4 means what in transformation? Stretch by 4, or a factor of 4. And then I attach a negative on the outside of the function. Negative on the outside of the function means what? Reflect x-axis. And then the next thing is what? I have a plus 4. But the plus 4 is outside of the function, so up 4. So this is how you get from f to g.